All right, so yesterday I uploaded problem set 3 on imparters, and we will discuss these questions tomorrow in the tutorial session. And these questions are based up to the definition of the stress tensor, which I covered in the last class. And also I will review during next 5 minutes, I will review the definition of that. So lecture wise, we are ready to attempt solving those problems. I hope I am audible. Somebody may please confirm. Okay. All right. So last class I was saying that to be able to draw the free body diagram of that fluid element which is currently occupying the control volume of our interest, we need to identify all forces. Okay. In fluid mechanics, we classify all those forces which are acting on this fluid element. What I've shown here on the right hand side, we classify the forces under two headings. One is body force, the other is surface force. And mind you, this segregation is, as I have highlighted here, only for the external forces acting on the fluid element. Okay, so this segregation is not in isolation. It is with reference to this fluid element, and only external forces are being considered for this classification. So body forces, to remind you, are those external forces, and again I am highlighting external to the Fe currently occupying the control volume, those external forces that act on every fluid particle of the fluid element. So it doesn't matter where that fluid particle right now is inside this fluid element. It could be on the surface of the fluid element, one of the 6 surfaces, or it may be well within or inside the fluid element. That those forces, body forces, act on all of them. Good example is gravitational force. It doesn't matter where the fluid particle is, it will experience this external gravitational force. Whereas surface forces are those external forces that act only on those fluid particles which are not act should not be here, which are on the surface of the fluid element. And who exerts these surface forces? The fluid particles in the neighborhood of our fluid element, and which are not part of this fluid element. They are exerting those forces on the fluid particles of our fluid element which are on the surface. Okay. So as far as body forces are concerned, we can represent the sum total of the body force, vector sum total of the body force acting on each fluid particle, as one single vector acting at the center of mass of the fluid element, right? Q is the center of mass of fluid element. So that's what I'm presenting F as the net body force. Now, if body forces are such that they have a non-zero net moment of a couple also, then that should also be presented here as a moment due to a couple. But as I said in the last class, most of the times we deal with fluids which do not experience any body couple, so-called body couple. So in other words, what I'm saying, most of the times we will be dealing with fluids which experience body forces whose equivalent is a single force vector acting at the center of mass with no couple. Like again, gravitational force. You don't have to put any couple at the center of mass. So this will be the representation, just one single vector for body forces. So that is taken care of. How do we represent surface forces? So we represent surface forces using the stress vector, stress tensor, for which I am using the symbol sigma. Okay, again, this is recap. So I hope you had a look at the notes earlier also. So I will go a little fast since it's recap. So stress tensor is defined at a point in the flow domain. So in our Cartesian coordinate system, stress tensor will be a function of independent variables x1, x2, x3, and t. Now, stress tensor is a second order tensor. So it will have 9 scalar components. And here in this slide, I'm trying to explain what these 3 components mean: 1, 1, 1, 2, and 1, 3. And again, once you understand the definition of these 3 components, I'm sure you can extend that understanding to explain other components like sigma 2, 3 or sigma 2, 1, and so on. So what is the meaning of, what are the meanings of these terms? As I was explaining in the last class, if the point under consideration is x1, x2, x3, t, x1, x2, x3, you imagine a plane which is perpendicular, which has its normal along one direction, and you make 2 imaginary cuts in the fluid. Okay, you take the left part, consider an area delta A there, and there should be a delta F force acting on the left part through that area delta A. Who is exerting this delta F force? The part that was on the right. Okay, so initially that was an internal force. If you consider the whole domain as system, if you make a cut, take away the right part, the force that is appearing now, delta F, is external force acting on the left part. Now that force delta F vector will have in general 3 components, what I have shown here. Okay, then sigma 1, 1 is defined as what I have shown here: delta F1 by delta A, limiting value delta A going to 0. Sigma 1, 2 is defined limiting value delta A going to 0, delta F2 by delta A. So the first index is actually telling us the orientation of the plane, or normal to the plane, which has been used to make this imaginary cut to divide the fluid mass into 2 parts. One corresponds to E1, and the second index corresponds to the force component acting on that area delta A of the left part, as I have shown you. Okay, so this is the significance of 2 indices. Similarly, sigma 1, 3 will be limiting value delta F3, delta A going to 0. All right, so similarly, physical meanings of 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3 can also be interpreted. When the body force is being acted on a FE, do internal force come into play? What do you mean by internal forces come into play? I mean, uh, we are trying to identify all external forces acting on fluid element. So that's what we are identifying, because very soon we are going to apply Newton's second law. So we need only external forces. Internal forces may be non-zero. In general, they will be non-zero, but they are acting on one fluid particle, which is part of fluid element, to another fluid particle, which is also part of fluid element. So those forces are there, but they are of no consequence when I am identifying external forces on the FE, because they will cancel out in pairs. Have I answered your question? Okay. So you said in quiz syllabus will be 23, but 23 is a holiday. Yes, I also realized this. I realized this this morning. So of course, then I will say quiz will be based on whatever we cover up to tomorrow's lecture, which will be I think lecture number 13. All right, Mokshit. Yeah, in fact, there is no class this Friday. There is no class even on Saturday. So this week we have only 2 lectures. I will send an email also today to make it more official that quiz will be based on whatever we cover till Wednesday tomorrow. Okay. I also talked about sign convention for sigma ij components. So this I am emphasizing to highlight that the sign of sigma components, sigma 1, 1 or 1, 2, etc., that doesn't really correspond directly. I mean, that is not the same as the sign of delta F component. Okay, area also plays a role. So it is the combination of the orientation of the area on which the small force acts, as well as the direction of the force components, which together decide the sign of sigma ij. So the rules are, and this is a matter of convention that we all follow. Sign of sigma j is positive if outward unit normal is along E1 direction, EI direction, and delta fj, both should be satisfied, and delta fj is along positive direction. If both are along positive direction, then sigma ij is positive. Also, sign of sigma ij is positive if outward unit normal is along EI direction, and delta fj is also along uh, is along negative EI direction, and delta fj is also along negative EJ direction. If these two are not followed, then sigma ij will take negative sign. I gave some examples here. On this surface, unit normal is positive, force is positive. I will conclude sigma 1, 2 is plus 5 SI units. On this surface, unit normal is negative along negative E1. Force is also along negative E2, still positive, sigma 1, 2. Whereas in this case, if unit normal is along plus E1, but force is along minus E2, then I will say sigma 1, 2 is minus 5 SI units, which is Newton per meter square. Okay. So this much I covered in the last class. To further give you examples on this sign convention and to ensure that you understand it fully, I have added a couple of more slides. So again, this is the whole fluid domain. This is a reference frame. Go to a location. That location has coordinates x1, x2, x3. Sigma is defined there. Now P and P prime, and now you take an imaginary cut using this surface which is perpendicular, which has unit normal along E1, and imaginary, in your imagination you separate the two parts, left part and right part, and P and P prime are points which have coordinates x1, x2, x3. So P belongs to the left part, P prime belongs to the right part. Originally they were right next to each other, same x1, x2, x3. So as I said, sigma is defined for point. Okay, so sigma 1, 1 will be 5 for P. It will be 5 for P prime also, because they are the same points. Okay. But sigma 1, 1 equals plus 5 means force along E1 on a surface with outward normal E1. Okay. So on this surface, which is outward normal along E1, the force is 5 times delta A along this direction. So this I am showing direction of force. But if you go to the other surface, which has unit normal along minus E1 direction, the same sigma 1, 1 equals 5, positive 5 actually is telling me that the force acting, external force acting on this delta A on this side, on the right hand side, is actually along minus E1 direction. Okay. So if you want to draw free body diagram of left part, your force appearing because of sigma 1, 1 should be pointed towards right. If you have to draw free body diagram of the right part, the force, that external force that you should put corresponding to sigma 1, 1 should be acting towards left. Same idea for a similar idea for sigma 1, 2. If sigma 1, 2 is 3, it is 3 for both P and P prime, because again it is defined for a point. But if you have to draw free body diagram of the left part, sigma 1, 2, 3 means that the force acting in the two directions should be pointed upwards. And if you are drawing a free body drawing the free body diagram of the right part, then the force that you should draw corresponding to sigma 1 to 3, sigma 1 2 equals 3 should be pointed towards minus E2 direction. That is following the sign convention. Okay, so with this idea, now having defined sigma and its sign convention, now we go back to our original quest, which was to draw the free body diagram of the fluid element, which is currently occupying our control volume. Okay, so we draw a BD of this Fe as our system, and this is what it will look like. A lot of terms are there. I will keep this slide for a minute, and I want you to pay attention to various indices of sigma on various surfaces and derivatives that are being used. So remember that all sigma values, sigma 1, 2, 1, 1, and their derivatives are all at point Q. Okay. And then this fluid element has dimensions delta x1, delta x2, and delta x3. This is the orientation. These are the orientations of our 3-axis Cartesian coordinate system. Accordingly, this is delta x1, and this is vertical is like delta x2, and coming out of the plane is delta x3. So using the values of sigma and their derivatives at the center of the control volume, or center of mass, center of the fluid element, or center of mass of the fluid element, I am writing on the right face, okay, I am writing the various forces that will be arising or that will be acting on the fluid element corresponding to the surface forces. So surface forces being represented by stress. So in one direction, on surface 1 in one direction, what I have, so sigma 1 1 should be relevant. On one surface along one direction, sigma 1 1 should be relevant. On one surface, or a surface perpendicular to E1 along two direction, if I want to find force, sigma 1 2 will be the relevant component, right? And on a surface which is perpendicular to E1, if I have to write forces acting in the third direction, sigma 1 3 component should be relevant, right? And then I am bringing this derivative term because these values 1 2 1 1 and 1 3 are actually at Q, but I am on a surface which is delta x1 by 2 displaced from the center of mass in the direction of E1. Okay, so Taylor series I am using with delta x1 2 displacement you see here, and all these this displacement is along one axis. That's why partial with x1 in all of them. So whatever is in parenthesis, that is the value of here, value of sigma 1 2 on this surface. Okay, and then I want to get force, I multiply by the area of that surface, this surface, which is delta x2 times delta x3, and that appears everywhere. So this gives me three forces, three components of the surface forces acting on my fluid element through the surface, which is delta x1 by 2 displaced in plus E1 direction. Hope it makes sense. This is a very important step to write these expressions correctly if you want to get the free body diagram correct, and in turn if you want to get the governing equations correct. So you must ensure you understand and you agree with various things that are appearing on this slide. So this is these are all the three forces, three components of forces acting on surface, which has outward normal along E1. Now, if you go to the other surface, opposite surface, which has perpendicular along E1, but outward normal is minus along minus E1, right? Outward normal is along minus E1. So see, the expression there has two differences. First of all, in Taylor series approximation on the right hand side, we had plus plus. I mean, derivatives were coming with plus sign. Here, derivatives are coming with a minus sign, right? Because this surface is on the minus E1 direction, displaced from Q in the minus E1 direction by delta x1 by 2. So that takes care of the minus sign. Area is the same, delta x2, delta x3. But pay attention to this detail that the direction of forces acting on this side, I mean the left face, directions are being drawn in the opposite direction, as the directions of forces are opposite as compared to what we had on the right face. So sigma 1 1 minus del sigma 1 1 del x1 delta x1 by 2 delta x2 delta x3 is indeed the force component acting along E1 on this fluid element through the left surface, but the direction is pointing away from the surface. Or I should say it is along minus E1 direction. Similarly, 2 force, what you are getting with sigma 1 2, using sigma 1 2, that is being presented with a downward arrow which is pointing in minus E2 direction. And the force that you are getting with force component that you are getting with sigma 1 3 component, that is being drawn pointing in the negative E3 direction. Okay, and this is this opposite sense has been put here on the slide, keeping in mind what I explained on the last two slides. So sigma 1 to 3, the same value will give you a force along, means a force along plus 2 plus E2 if the outward normal is along plus E1. But if the outward normal is along minus E1, the same value sigma 1 to 3 actually means a force that is acting along minus E2 direction. That is the idea that has been used here to draw the arrows in the fashion they appear on this slide. Okay, any questions on this? Can you explain del x1 term? Yes. I think you are referring to this. In the negative in the del x1. You're referring. So minus is appearing here because again you see I'm using Taylor series expansion to find the value of say sigma 1 1 on the left face, right? Since I'm using Taylor series, I'm using value of sigma 1 1 at a base location. That base location is Q. Okay, so sigma 1 1 first term appears because of this being the value of sigma 1 1 at Q itself. But then I want the value of net sigma 1 1 on the left face, which is located at minus delta x1 by 2 from my base location. So you recall in Taylor series, if you have delta x1, if you replace by minus delta x1, that sign will appear here, right? That's how it is coming. I hope I have answered. If not, let me know. I will make another attempt. Okay. All right. Any other question? Any other question? Okay, so this is okay. So this free body diagram that I have drawn, I'm trying to draw. Clearly, you see, I'm trying to draw forces in all directions. Very soon, I will focus only on the forces acting in one direction. But right now, it is wherever I go, on whichever face I go, I have drawn or I have written the expressions for all the three components of forces. You can continue this exercise for all faces. I have put what is happening on the top face also, and let me go over it since I have put it here. Let me go over it, and I hope it will consolidate the ideas that I have presented so far. So on the top face, this face, which stress components will be of significance? Those stress components will be of significance which have the first index as 2, right? Why? Because the first index represents the area or identifies the area. So the area on which I am when I am focusing on the top surface is the area which has unit normal along E2 direction. And that's why only those sigma components with first index as 2 will be of relevance. So you see I have 2, 1, 2, 2, and 2, 3. Those are the three components which are to be considered or which play any role as far as the top surface is concerned. Again, I want to use the values of sigma 2, 1, 2, 2. So sigma 2, 1, that the second index, when the second index is 1, it will give me the force along one direction acting on this surface. When the second index is 2, this will give me the force along two direction. And when the second index is 3, it will give me the force component acting on this surface along three direction, right? So 2, 1, 2, 2, and 2, 3 are significant. But then again, this realization that the top surface is away from my base location as far as Taylor series approximation is concerned. It's away from the base location Q in, what is the displacement? How far is it? It is plus delta x2 by 2 away from Q. And along two directions. So you will have derivatives with respect to 2, right, of all the components multiplied by delta x2 by 2. So these will be the stress values on this surface. And then the area of this top surface is delta x1 times delta x3. So that's what is appearing here. Now note here that the forces corresponding to these stress components excuse me. Note that the forces corresponding to these stress components are placed at the center of the corresponding faces of the fluid element. So you see I have placed these forces, these arrows, at the center of these faces, and this is a good approximation if delta 1, delta x2, delta x1, delta x2, and delta x3 are small. Again, there is this idea of first order approximation. So all these three dots represent the center of the faces, centers of the respective faces, and that's where you place these forces. So in reality, there is on every face there is a continuous distribution of force, right? But then you can think of this as I am removing all those distribution of forces on each face, and I am representing that force system by an equivalent force system which has only three concentrated forces acting at the center of the face. And as I said, this approximation is very reasonable if these faces have small dimensions. If the face dimensions become large, this may not be accurate, putting equivalent forces, concentrated forces on the centers. All right, so I hope with whatever I have written here, when you read, you will get an idea and you should be able to answer a question if somebody asks, show me a small fluid element and draw or write the expression of various surface force components acting on which various surfaces. So if somebody asks a question like this, you should first ask which surface, on which surface you want the force component. So he will tell you on a surface which is perpendicular to E3. Then you know that sigma 31, sigma 32, and sigma 33 will be important. Then you use Taylor series appropriately, multiply by appropriate area, and show the arrows in the right way, as I highlighted earlier. So on a surface with positive E1, the direction of forces, on a surface with outward normal as positive E1, the direction will be like this. On a surface with outward normal along minus E1, the direction of the forces should be reversed. So that would be your complete answer to a question of that sort. Okay. Okay, so now we go back to deriving or drawing the free body diagram of the fluid element to identify forces only acting in one direction. So that's what I was doing in the last class. I was trying to apply F equals ma, Newton's second law, on this fluid element in one direction, because I was accounting for changes in one momentum of this fluid element. So if I have a body force, if we represent body force as this vector v1 e1 v2 e2 v3 e3, where this is, mind you, body force per unit mass. So in fluid mechanics we use body force per unit mass. I mean, that's what appears in the governing equation. It's not body force absolutely, but body force per unit mass. So to get the absolute body force, I will have to multiply by corresponding mass of the fluid element. That's what it is here. You see, so net external force, net external body force in one direction will be B1 times rho density multiplied by the volume. Okay, so this is nothing but the mass of the fluid element under consideration. So this is the body, this gives me the total body force acting. So this is one force. What are the other forces? The other forces in one direction. So if I have to account for surface forces along one direction, I should go to individual surfaces first and I should go to first surface and get the force, external surface force in one direction. I should go to surface 2, go to surface 3. One by one I should go and keep getting the force, external surface force acting in one direction, right? So that's what I've done here. You see there are 6 parts of the external surface force acting in one direction. The first is what I've written, S1 means this is the external surface force which is acting on surface 1 of the fluid element, which is here, and then 2, then 3 the top surface, 4 bottom surface, 5 the front surface, and 6 is the surface behind us. Okay, so there are 6 terms here. If you focus on one is nothing but what I drew here, right? Sigma 1 this term, middle term. This is what on surface 1, if you are drawing free body diagram only for one direction, then this is the only component that matters. 1, 2 and 1, 3 do not matter. Even though they are acting on surface 1, these forces are in 2 and 3 direction. I am not paying attention to those right now. I want only force in one direction. So this is what I have. So this is what I have written here. I go to surface 2. Again, there are 3 forces, but what is of relevance to me is only this one direction. I have put it here. Now, again, pay attention here that the force that is coming because of stress tensor, what I have written here, that comes with a positive sign. But then the force that is a force that we wrote on the expression that we wrote on for S2 surface here, mind you, it is pointing towards left, minus E1. So when I am trying to find net force in one direction on the Fe, I should put a minus sign here. Okay. So there are 2 minuses. One is minus because of Taylor series, and then there is one minus because that force is actually oriented in minus E1 direction. So S1 and S2 contribute this much surface force along one direction. I go to surface 3. Surface 3 has outward normal or has outward normal along 2 direction. So Sigma 21 is of relevance, not sigma 22 and not sigma 23, but 21, because I want one force on two surface or unit normal along one force on the surface which has unit normal in two directions. So sigma 21 is here. This is the force that is coming, that is being exerted on the top surface, and this is the force that is being exerted on the bottom surface. And since in the on the bottom surface this force is pointed towards down or minus E2 direction, I have put minus here to get things algebraically correct. Same as the idea for sigma 31. I will leave this slide for a minute. Just for trying to clarify, this is free body diagram with accounting only for forces that are acting in even direction. So this free body diagram is not complete, but that's what I need for the time being. Okay, questions? Okay. So if we are comfortable with these terms being written in this fashion, and if we are comfortable with signs and all, then we can see that if you combine S1 and S2 algebraically, sigma 11 actually gets cancelled out, right? What you are left with is what I have shown here in green color. So this is the net force acting on the Fe in one direction because of the surface forces acting on surfaces 1 and 2. Del sigma 11, del x1, delta x1, delta x2, delta x3. So actually sigma 11 doesn't matter. It's the derivative of sigma 11 with respect to x1 that decides the force in one direction because of 1 and 2 surfaces. Similarly, 3 and 4, whatever we have, you can see that this will simplify to del sigma 21 del x2, derivative of 21 in the second direction that decides the net force acting in one direction because of surfaces 3 and 4. And similarly for 5 and 6, it is del sigma 31 derivative, partial derivative with x3 multiplied by delta x1, delta x2, delta x3. Okay. So these are the net forces, surface forces. Body force, I have just drawn them here directly with expression also written. B1, whatever I had here. Again, it's I know it's a little confusing. I should not write this here because I said I am paying attention to only forces in one direction. So please ignore this. So in one direction, only this matters. B1 rho, delta x1, delta x2, delta x3. Okay, so it's quite a handful of expressions or terms we had, but eventually things become, and dust settles down. Algebra is simpler than what we started with. All right. So now with this, these forces in our hands, the expressions of these forces in our hands, I go back all the way to my what I have been referring to as the starred equation. Okay, in the starred equation, which when we set phi in the starred equation that we derived last week, if you put phi equals rho v1, this is what you get on the left hand side, and reason 2, which is the non-flux reason. The reason why one momentum should change inside the control volume. First, this bunch of terms, we know that is because of flux reason, and all non-flux reasons are combined in reason 2. And then we also reasoned out that the reason 2 for momentum should be the net force acting on the fluid element in one direction. So that's what I'm writing here. Reason 2 is the body force, net body force acting on the fluid element in one direction, and then net surface force acting on the fluid element in one direction. This is surface and this is body. And the way we had cast this starred equation, this volume was in the denominator, and you see that is going to be taken care of in the way that it is also appearing in the numerator, though, so it cancels out, and what you are left with is this equation, what I am referring to using this 1, Roman 1. All right. So we have gotten our second partial differential equation which governs fluid mechanics. Of course, we have introduced new unknowns, sigma. We will see soon what does sigma depend on in fluid mechanics. We will see that later, but at least we have an equation. We have an equation with no languages anymore, no reason 2, reason 1. We have mathematical expressions and symbols appearing. Now let us simplify this equation a little bit, because many times in textbooks you will see a simplified form of the left hand side. Equation is the same, but a simplified form of the left hand side. So I want to do this exercise here. So recall that earlier I derived this equation, mass conservation equation. Go back to the notes, Saturday notes, you will see that this was the equation we have already derived when phi was equal to rho. If you multiply both sides of 2 by v1, okay, multiply both sides of 2 by v1, you get what I have written here, that becomes 3. Essentially, I'm trying to make the left hand side a little less cluttered. That's what I'm trying to do, and that's what many textbooks use for later references. So if I multiply 2 by v1, this is what I get, and then I'm going to subtract this equation 3, what I got by multiplying 2 by v1. I'm going to subtract 3 from 1. Subtract 3 from 1. So you will see that on the right hand side, when you subtract 3 from 1, nothing will change in 1, because the right hand side of 3 is 0. So the right hand side of 1 will remain unchanged, but we can make some simplification on the left hand side. What simplification we can make? You see here we have partial of time acting on the product of rho v1, and here I have v1, product of v1 acting on partial of density. So if you subtract this 3 from 1, what we will be left with? We will be left with rho coming out of partial derivative, and then partial of v1 with time, right? And such a thing should happen with other terms also. So what you will finally get is, if you do this subtraction on the left hand side term by term, you should get this form of the equation, what I'm showing in green box. So effectively, I have taken a row out of the derivative. Partial derivatives are partial with time on the left hand side. Okay, and then many times we keep row on the right hand side. I mean, I'll just for I mean, you will see this form more often. That's why I have done it. Otherwise, it doesn't make any difference. The equation remains the same. Divide throughout by row, and this is what is the form of equation we finally get. So this is the statement of Newton's second law in one direction for fluid mechanics when your description is Eulerian. Okay. So having arrived at this, so this was for rho v1, right? One momentum. I should get equations for second two momentum and three momentum as well, right? Because they are scalar components. Well, momentum is a vector, so we should have separate equations for the three components of the vector. So I want to get similar equation for V2 and V3. The two choices are there, the same two choices. You can either go back to free body diagram, derive everything for two momentum from first principles, from very first step, or we can look at the pattern and can write the equation for V2. Okay, that's what second option I'm going to choose. Can we write the second equation directly based on the pattern seen in the first equation? This way. Okay, so what is the pattern? V1 will change to V2. I will just let you have a look at it. I hope you see the pattern here, what is happening. Not much point saying things in words. And again, anything you are not convinced that this pattern has been recognized correctly, you are always free to go back and do the full derivation. And then maybe you will, next time onwards, you will feel confident to use this, just use the pattern to write the equation. So this is for V2, and similarly, we can get equation for V3 here. Okay, so right hand side body forces, here it was B1, here it is B2, here it is B3. Partial x1, x2, x3 are in all of them, because you will go to all the six faces to find the forces. But what components you will appeal to or what components you will bother depends on which momentum you are talking about. So here sigma 1, 1, 2, 1, and 3, 1. Here sigma 1, 2, 2, 2, and 3, 2. So the second index is telling me which component of momentum I am worrying about. And here you see it is 3. And the first index is supposed to tell me on what area or surface, what surface of the fluid element these forces are coming from. So every force component should come from all the surfaces. So that's why the first index remains the same in sigma in all the three equations, but the second one is what changes, deciding the direction of the forces considered for that component of momentum. All right, so we have applied conservation of mass, and we have applied Newton's second law in all three sides. So two natural laws we have used. There is one more left, which is the first law of thermodynamics, which we will see later. So on this slide, I have summarized the equations that we have obtained so far. So this 2 is what I derived today, 3 I recognized, I found by pattern recognition, 4 also by pattern recognition. These equations are also referred to as, you can call them one momentum equation, or sometimes we also call them V1 equation, what I derived today. It is the partial derivative PDE, partial differential equation governing V1. This is called equation for V2, second one, and the third one is called V3 equation. V1 equation, V2 equation, and V3 equation. And the first equation is what we got from conservation of mass. Now that equation sometimes is also cast in a slightly different way. Equation remains the same. So this is what we derived, what you see here. Many times what we do is we apply product rule of differentiation on the individual partial derivative terms, and we keep this terms like this on the left hand side and take the remaining part on the right hand side. I hope you will be able to recognize what this is. This has an identity we have already seen before. This is nothing but V dot. This is the advection operator acting on rho. Right? So since it is represents advection operator and it has some physical meaning, which I have discussed earlier also, that's why some people prefer, and we will also prefer, uh, rewriting this mass conservation equation in this form, in which the advection and the partial derivative terms remain on the left, and whatever is remaining, we take on the right hand side. So that's what I have written here, and that is this equation is also called continuity equation. The mass conservation equation is also called continuity equation. You can also call it rho equation because it is the governing equation for density. All right, so we have these four equations that we have derived so far. So I stop here. If you have any questions, can. So there's a lot of algebra we have been doing, especially today's class, all algebra, but can't be helped. You have to derive it at some point, and this is the right time in my understanding. So it is unavoidable. Later, of course, we will keep trying to get more physical meanings as much as we can, but this derivation and this much of algebra we have to deal with. So I'll be here for next 7 minutes. Anybody has a question, please type your message. Since there are no more questions, so I will let the session end on its own in next 1.5 minutes. I'm not going to extend this.